Pictures, all right. So I would say that this integral, it's real easy to see what the limits of integration are going to be. We're starting, well, if we're using vertical cross sections, which I probably would. I probably would use vertical cross sections in general, unless there's a good reason not to. So all things being equal, vertical cross sections. So the area is going from 0 to 8. But what do we integrate? That's kind of the crux of this question, is what actually is the equation of that line? Well, we can see it's a line. We can see what the slope is, I think, right? The slope is 16/8, which is 2. So I think it's not too terrible to see that this line is the line y equals 2x. And so we're just integrating 2x from 0 to 8. And I'm not going to do it because the problem said just to set it up. Although we could totally do it, right? It'd be x squared, you plug it 8, 0, 64. What I really want to ask here is, now I want to set up an integral for the volume that we get by revolving this around the x-axis. This region around the x-axis. And so again, I'm going to point out, right, when you're looking at the area, you're thinking of this as the height of your rectangle and this as the width of your rectangle. When you're doing volume, you're rotating this thing around. And so you're rotating this thing around, and now it's going to look like a little disc. And so instead of integrating the height times the width, now we're going to be integrating the area of the disc times the width. And the area of the disc is a circle. So our volume here is going to be still the integral from 0 to 8, right? No matter if we're doing rectangles or discs, we're still going as far left as 0 and as far right as 8. And now it's going to be, instead of the height of our rectangle, it's going to be the area of our disc, or the area of our circle, if you prefer. And the width is still the width. Now, here's what's interesting about this. If you rotate this thing around, like you rotate the whole shape around, I guess I can draw it over here. What kind of shape do we get? Yeah, it's a cone. And there is a formula for the volume of a cone. You may or may not know it. The formula for the volume of a cone is 1/3 pi r squared h. Where in this case, this would be the quote unquote radius, and this would be the quote unquote height. So it looks like our height would be 8. Our radius would be 16. And then we could totally use this formula to figure it out. It'd be some gross number. It'd be 1/3 pi times 16 squared times 8, whatever that is. But you would also get the same thing if you did it this way, or you should. So if we integrate this, it's the integral from 0 to 8 of pi times 4x squared dx, which ends up being pi times 4 times x cubed over 3 from 0 to 8, which ends up being pi times 4 times 8 cubed over 3. So the question you have to ask yourself is it true that this is the same as 1/3 pi times 16 squared times 8? And I think it is. Let's see. Here I have an 8 times 8 times 8 times 4. Here I have an 8 times 8 times 8 times 2 times 2, which is 4. Yeah, it's the same, which it should be. So this is how you would actually use an integral to find the volume of a cone. It's kind of neat. You can do the same sort of thing to find the volume of a sphere. So let's do that, because it's kind of a question on your homework. So what if I wanted to find the volume of a sphere? Actually, I should really say we're gonna set up the integral to find the volume, because if they just said find the volume, you can totally just use the volume equation. But if we say set up an integral to find, set up an integral, then you kind of have to do the thing they want you to do instead of just using the volume equation. for the volume of sphere of radius 6 centered at the origin. So here's the idea. We're not going to take a sphere, we're not going to start with a sphere, just like we didn't start with a cone previously. To get a cone, we started with a triangle and we revolved it around the x-axis. To get a sphere, we're going to start with not a circle, but a semicircle. We're going to start with a circle of radius 6. And we're going to revolve that around the x-axis. Okay. So same idea as always when you're checking my volume. We're just taking this thin little strip, revolving it around, getting a disk, and adding up all the disks. So here, the limits of integration are going to be from -6 to 6. We're going to go as far left as there, as far right as there. And then the very general way of doing this is just saying, okay, the integral is pi times my radius squared times dx. The real, I don't know, the challenge part here, or the part that's the hard part, is to actually figure out what is the function of this circle. Well, the way I would probably start if I didn't remember, I don't remember what it is, to be honest. What I do remember is that I know the equation of a whole circle. It's x squared plus y squared equals the radius squared, assuming we're centered at the origin. Solving for y squared equals 36 minus x squared, y equals the square root of 36 minus x squared. I should really say it's plus or minus, but the top half's the plus part, the bottom half's the minus part. We want the top half, so yeah. And then we jam that in for our radius. And look how nice this turns out. It's the integral from -6 to 6, bring out the pi, and I've got the square root of 36 minus x squared squared, which is just going to be 36 minus x squared. That comes out real nice. -6 to 6 of 36 minus x squared dx. I'm going to do one thing, just not because I really want to, just to show you that people do it. Instead of doing this, I'm going to do this. I'm going to write this as 2 pi times the integral from 0 to 6 of 36 minus x squared. Why am I allowed to do that? Right, or the words I would use, but you're totally right. It's an even function, right? But right, it has symmetry across the y-axis. Same idea, literally the same idea. So since it's an even function, we can totally cut it in half and then double it to get the same thing. So then we have 2 pi integrating 36. I know I said setup, but I'm going to finish it because I want to see what it looks like. So you get 36x minus x cubed over 3. And if we plug in 6, we're going to get 2 pi times 36 times 6, which is 6 cubed, which is what I'm going to write, minus 6 cubed over 3. And instead of actually thinking about what 6 cubed is, although it's not too terrible, we could factor out the 6 cubed. So this is going to be 2 pi times 6 cubed times 1 minus 1/3, or 2 pi times 2/3 times 6 cubed, or in other words, 4/3 pi times the radius cubed, which is the volume of a sphere of radius, whatever. Kind of cool. It is really cool, actually, I think. That's another thing. So these volume questions, they all kind of boil down to the same process. The only thing that gets kind of ugly sometimes is maybe your region is total garbage. So maybe, and I'm looking at some of these, I'm looking at you homework problem. Let me grab one of these that has like real trash in it. That was not so bad. Oh, there was one here. Actually, there was one homework problem from the next homework assignment that's due. I don't know, is section 5.7 due today? No, he moved stuff back. Okay. He or she? She, sorry. I don't actually know this teacher. I should just say that. So problem 14 on the next section, I just want to point out, has something that's worded in a way that I feel like could be confusing, so I just want to address it. So here's problem 14. I'm going to change it a little bit. Find the volume of the solid obtained by revolving the region, because there's always so many words to write. The region bounded by, also, by the way, those of you on Zoom, if you have questions, don't hesitate to like throw them at me. I'm happy to address questions. Bound, but you guys too. I think you know that by now. By y equals x squared, y equals 0, x equals 0, and x equal to 49. So here's the issue I have with this particular region. And this one I want to point out to you might feel confusing. I have said, and it's usually correct to say that when we're trying to draw the region, it should always have each of these graphs that are boundaries as boundaries. But here's the problem with this. We draw this. Here's my usual coordinate system. And right here's y equals 0. Here's x equals 0. Here's y equals x squared. And here's x equals 49. And I feel like the problem here is that x equals 0 isn't really one of the boundaries. We didn't really need to have said that. It's certainly one of the limits of integration, but you could have totally said my boundaries are these three things, x squared, y equals 0, and x equals 49, and still been able to come up with this as the only potential region. So saying x equals 0, although it's perfectly fine, I guess. To me, it feels like the line x equals 0 should actually be a border, not just the point that happens to be the intersection of these other two graphs. So I wouldn't worry too much about it, but just in case you found that confusing later on, it's just kind of an oversight. I wouldn't say x equals 0, but I think what they're really trying to do is they're trying to give you the functions and then trying to give you like limits of integration. So they're trying to make it easy, but I felt like, to me at least, it it's confusing. So here, the area of this region, which I know is not what we're being asked to find, but I'm just going to point out, the area would be the integral from 0 to 49 of just x squared minus the bottom function. And then the volume, if we're revolving around, what are we revolving around? Oh, no, that's still fine. Yeah. Around the y-axis. So I'm going around the y-axis, I do have to use a horizontal cross-section. We should do more practice with the y-axis. It's a good idea. I'm using a horizontal cross-section. And since my cross-section doesn't touch my axis of rotation, right, like there's some distance between it, we know we have to use the washer method because we're going to be subtracting out the inner circle. So here, our volume is going to be pi times your big radius squared minus pi times your little radius squared times a dy. And that's the volume of our washer. You should do as much or as little drawing as you feel like you need to. I always like to try and draw a lot of the stuff. So like if I bring this down here, I'm thinking about my washer looking like this. If you don't want to draw that or not good at drawing it, you don't need to draw it. But that's the line of my washer, where here's my little radius and here's my big radius. The big radius is easy, just x equals 49. The small radius is a little bit more work. Instead of being y equals x squared, we have to solve for x and say it's going to be x equal to the square root of y. And then we toss it all into the thing. So the total volume is going to be the integral, let's factor out the pi, of 49 squared minus the square root of y squared dy. How low do we go? 0, definitely 0. How high we go is something that we would probably have to do a little bit of work to figure out. I mean, not a lot. If this point has an x coordinate of 49, the y coordinate is right. It's terrible. So look, those are gross numbers, and it actually wants to find the volume here. So the number is not much better on the actual problem. They use 36 instead of 49. So I mean, yeah, 49 really, James? That's 49. So but I feel like I need to double check here. Yeah, that's really 49. That's terrible. Okay, so 49 squared. That's awful. And then you would integrate away. You get pi times the integral of 49 squared is 49 squared times y. The integral of y is y squared over 2. 0 to 49 squared. Now, what I want to point out is just like in the previous problem, simplifying this down is not too tough. Now, you could totally just jam all this into web work, right? You could say that my answer is going to be plug in 49 squared. You've got pi times 49 squared. I guess 49 squared times 49 squared I could write 49 to the fourth minus 49 squared divided by 2. Okay, but and then minus 0 minus 0. Here's what you should see. You've got a thing minus half of a thing. I should say a thing minus half of the same thing. So if you have some number and you subtract half of it, you're left with the other half of it. So really we should just say this is going to be pi times half of 49 squared. Or 49 to the fourth. And that's what I would type into WebWork if I was trying to not do too much calculation work, but not type a billion things either. Why is it 49 squared? Good question. So when we're talking about doing horizontal cross sections, we have to go to the lowest, right? The bottom is the lowest y value, or how low it can slide. And that's definitely a y equals 0. And the highest point here is how high it can go, which is this point here, but it's the y value there. The x value is 49, unfortunately. The y value is, well, since this curve is y equals x squared, if x is 49, y is going to be 49 squared, which is kind of gross, but it's what we've got. And they picked, I feel like, I don't know, it seems like a bold choice for that one, but that is the number that we've chosen. Yeah. Other questions about this one? Okay. Before we do all the volume questions ever, not that we can't. Are there any last questions about the previous assignment that's due today? No? It's okay if there are, but it's okay if there aren't. Areas not, I mean, some of those problems, I would say the concept of area is not super confusing, right? Like it's fairly most of the time pretty straightforward, very qualified there, right? You're just doing the integral of top minus bottom or right minus left, whatever. The thing that's hard about some of your assignment problems is just some of the regions are gross looking, right? Like finding the thing you actually need to integrate or finding what your limits of integration are can be the harder part, but the actual anti-differentiating, not too bad. Okay, well, you're certainly welcome to, if you think of one you need to ask, you're welcome to ask it, but did you have a different question?
So, when they ask you to volume the
Yes. Sure. Well, so if we don't rotate, we just have a two-dimensional figure.
Area.
Right, exactly. So that's now I should say, another theory homework problems, at least for this assignment, all of our volume problems are volumes of revolution, meaning we are just taking some region and rotating around the axis. There are other ways of describing volumes, which it doesn't look like we're going to cover, so I'm not going to worry about it, but it's not the only way to talk about volume. It's just the way that is usually introduced because it's not too terrible. But what's really happening, so what I should say here is, right, this picture, if we actually were to draw it, it would look like, and I'm going to do my best to draw it here, although it usually comes out not great. So this region rotated around, let's draw it this way. So I would encourage you, if you're trying to draw these three-dimensional objects, not that you need to, you probably don't need to at all. But if you're going to, you're going to take the region you've got and reflect it across the axis of rotation. And I would say draw the outermost part bold, because it's like your outer boundary, but draw any inner parts as kind of dashed, because you're going to kind of be covering them up when you sweep the thing around. So here's what I mean. I'm going to draw this y equals x squared like this. And the idea is I'm going to rotate this around the axis. So I'm just kind of saying, okay, this is going to rotate around like this and then come back like that. But it's not just that, right? It's the whole thing. So I'm taking this, I'm also sweeping this out as well. Now here's where things are going to get dicey. Oh, geez, come on, you can do it, James. Okay, that's I should have. Okay, pretty good. Not too terrible. And so it looks kind of like this. And we've seen this kind of shape before a little bit. It kind of looks like someone took a solid block, like a log, and then scooped out a bowl from it. So you've got kind of this cool, I mean, it'd be a cool bowl to have, I think, this log thing you just made the bowl out of. But yeah, that's kind of what we've got here. It's some weird kind of bowl thing. But you can do this for any shape. So, or any, I should say, any region we want. For example, think of some other examples here. Sorry. There's some other papers. Are these the other papers I sent? I know I had other papers. Whatever. I'll find them later. Always having stuff for myself. I think they're down here. Yeah, they are. Okay, good. All right. Sorry. Try to keep them in order. Let's see, there was something else I was looking at before. Oh yeah, that looks terrible. Let's look at this one. Let's say we want to find the region. So we have the region R. So let R be the region bounded by the following. What have I got here? Y equal to x squared plus 21. Wow, I'll just write it this way. Fine. 21 plus x squared. Y equals 10x and y equals 40. Specifically, it says let it be bounded below by this. So this is the lower boundary. And above by these guys. These are the upper boundaries. And although, so if it were me, I would probably start by just trying to get an idea of what the graphs look like. So 21 plus x squared looks like your usual x squared graph shifted up 21. Okay, something like this. Y equals 10x is a line with a slope of 10. Now, the question that we kind of have to address is y equal 10x actually going to intersect 21 plus x squared? Right, because maybe it's steep enough that they're going to intersect, but maybe it's not steep enough and they're not going to intersect. So we should probably, before we draw, actually figure out if they intersect. So if I set x squared plus 21, wow, that's not how you write 21. That's how you write 12. 21 equal to 10x, and then bring everything to the left. X squared minus 10x plus 21 equals 0. And that does factor. Sometimes it doesn't. Sometimes they give you some real trash numbers and it doesn't factor. You get some gross square root quadratic formula kind of thing. But here we get both x equal to 3 and x equal to 7. So what's going to happen is this y equals 10x line is going to come up. Let's draw it in red. Here's y equals 10x. It's going to come up. It's going to hit this parabola somewhere, and then later on they're going to cross again. But since they said that the y equals 10x, well, actually we might actually need to see that. I don't know. Maybe we need to know where they get across again. Somewhere over here. And then y equals 40 is some horizontal line, probably below where they cross again. We can check. They cross again at 7. If x equals 7, what's the y value going to be? Well, let's see. 70 or, oh, they should be the same, 70, right? Then it is 70. So definitely y equals 40 is lower than where they cross again. So we've got something that's looking kind of like this. And we know a couple points of intersection. We know that this is the point 3 comma something. I guess we can figure out what it is. It's 3 comma 30. And we don't actually care about that point up there because again, right, the straight line and the horizontal line are the upper boundary and the parabola is the lower boundary. So it looks like we are looking at this region here. So I don't actually care about this point of intersection up here. I do care about this point here. I do care about this point here. That point there is easy to find. We're just setting y equals 10x equal to y equals 40, which is going to give us x equals 4. And over here, we're going to set 21 plus x squared equal to 40. And we're going to get x squared equal to the square root of 19. Or sorry, x squared equal to 19. Wow, good job, James. X squared equal to 19, so x is the square root of 19. So this point here is the square root of 19. And what are we doing? What are we doing? We didn't write I always fail to write the whole question because I get too distracted. We're revolving around the x-axis. Oh, what a bummer. And then so what's the volume if we revolve around the x-axis? And let me ask you all a very important question. If we're revolving around the x-axis, what kind of strips do we have to use? Say one more time? Washers. Well, yeah, washers. Yeah, yes, we're gonna use washers. So what orientation do our strips have to be? Oh. Vertical or horizontal? Vertical, because they have to be perpendicular to the axis of rotation. There's no other choice. Which is why I said it's a bummer, because if we have to use vertical ones, it means we're gonna have a break point. Right here, we're gonna have to split it up into 2 integrals. So our volume for this first section is going to be the integral from 3 to 4 of pi times a big radius squared minus a little radius squared dx, plus this next integral is going to be the integral from 4 to the square root of 19 of, again, the big radius squared, which is a new function, minus the little radius squared dx. So in this case, it's going to end up being pi times the integral from 3 to 4. My big radius here is the function 10x minus the little radius, which is x squared plus 21 squared, plus this one's going to be the same sort of deal. But now my large radius here is just the function y equals 40. So 40 squared minus the same small radius x squared plus 21 squared. Yeah.
I'm sorry, but could you just briefly explain real quick why you have split the area into two because of the x-axis?
Well, so let me show you why. So if we're revolving around the x-axis, we're using the disk / washer method. And really, I'm just calling them the same thing because they're the same thing. Specifically, though, it's the washer method here because our region is not flush with the axis of rotation, right? It's far away. So in this section here, before I get to 4, I'm drawing a vertical cross section. And so when I think about this vertical cross section here, there's my outer radius, which I write right. Ooh, there's my big thing, and here's my inner radius. And right, I don't want to draw the whole washer because I'm going to get in the way about this stuff. But the idea, right, is it's the big radius squared minus the little radius squared. And in this section, my big radius is the line y equals 10x, and my little radius is the parabola y equals x squared plus 21. But then we go to the other side of 4. Now this is my cross section, and the big radius is a different function. So I have to break it up because I can't just say it's right. I can't just do it as one integral. So that's it. That's why we don't love this, and why typically when you see a region where either the top part changes from one function to another part, or the bottom part changes from one function to another part, we have to break it up if we're doing with respect to x. Now I will say if we were going on the y-axis here, we could totally do it with one integral because using a horizontal cross section, the right function would always be this, the left function would always be this. It's kind of, but that's not what they asked us to do. So, bless you. The work for this is kind of atrocious. All right, I mean, so we've done the mental hard part of setting it up. The rest of it is not so much mentally challenging as just keeping track of everything and making sure you don't make a small error challenging, right? Doing this integral is fine, but just not nice, right? If we write this out, this is going to be pi times the integral from 3 to 4. 10x squared is 100x squared, and then x squared plus 21 quantity squared is minus x to the 4th plus 42x squared plus 441. And then the same kind of deal over here. We've got, don't forget the pi. I forgot the pi there. Ooh, that's dangerous. You never want to forget the pi. Pi is tasty. Don't forget it. We're adding on pi times the integral from 4 to the square root of 19 of 40 squared, which is 1600, minus, again, x to the 4th plus 42x squared plus 400. Plus 1. It just looks awful. Now, here's one thing I will say that you could do to maybe make this suck just a little bit less. You don't have to do this though. You can see that both of these integrals have this second part being the same. So if you really wanted to, you could write it this way. Now, just watch this for a second and we'll talk about it. So I'm going to break this up into 4 integrals, even though that seems terrible, but just hold on. Let's factor out the pi completely, so we don't have to think about it every time. So I'm going to have the integral from 3 to 4 of 100x squared dx minus the integral from 3 to 4 of all this stuff. Oh, that's a good idea, James. I just thought of something we could do, but I don't know if we want to. And then plus the integral from 4 to 19, sorry, square root of 19 of 1600. And then finally, minus the integral from 4 to the square root of 19 of the same x to the 4th plus 42x squared plus 441. Come on, sorry, terrible. Here's what I'm trying to say with a lot of words. You can kind of put these two things together, and you can say specifically that this and this together is really minus the integral from 3 to the square root of 19 of x squared, x to the fourth plus 42x squared plus 441. If you have an integral from something to something and then another integral from the end of this one to some other point, you can say, well, you're really just going from 3 to the square root of 19. So that's maybe a little less work as far as actually evaluating this thing. So if you wanted to make this maybe suck just a tiny bit less, you could write this as pi times the integral from 3 to 4 of 100x squared plus, sorry, dx, the integral from 4 to the square root of 19 of 1600 dx. Be careful, I thought that d was a 0 there for a second, I almost wrote 16,000. And then finally, minus the integral from 3 to the square root of 19 of x to the fourth plus 42x squared plus 441. But then it really is just awful. We integrate everything, we get pi times the integral of, let's see, 100x squared is 100 x cubed over 3 from 3 to 4 plus 1600x from 4 to root 19 minus x to the fifth over 5 plus 42x cubed over 3. 42 over 3 is 14 plus 441x from 3 to root 19. So at this point, you plug the numbers in and then you try to just write it into WebWork. You don't try to simplify this. Now I will say, if you can use a decimal approximation, now might be the time to do that, even though that's not my, I don't love that. It's not my favorite, but this might be the time where you're just like, screw it. I don't want to like do all of that. That's a lot. So that's what I would say. Fun times. Questions about this? Let's look, just because I think it's worthwhile, let's look at what we do if we were going around the y-axis, which is a much better question, I think. So let's look at the same region for just a moment. We're now around the y-axis. Here's our region again. So there's our region. We found these points. This was the point 3, 30. This was the point 4, 40. This was the point 4, square root of 19. No, sorry, square root of 19, 40. Apologize. Right. Yeah. And this was the function y equals x squared plus 1. This was y equals 40. This was y equals 10x. But now let's say we want to find the volume of the thing rotated around the y-axis. Not nearly as bad to set up. So if we're going around the y-axis, our volume is going to be, well, again, still washer method, because we have an inner radius and an outer radius. And it's going to be pi integral of big R squared minus little r squared. I do think when you're doing these volume integrals, it's really good just to write, if it's a disk method, pi integral of big R squared. If it's a washer method, pi integral of big R squared minus little r squared. It'll help you remember that you're just finding the thing that's further away and the thing that's not as far away. And then our limits of integration are also pretty easy to see from the graph. This is going to go as low as y equals 30, as high as y equals 40. So the only thing to do is to take our big radius and our little radius and write them in terms of y instead of in terms of x. So for y equals 10x, it's pretty great. It's pretty easy. That's our inner radius. For y equals 10x, we're just going to get x equals 1/10 y, or y divided by 10, whichever way you want to write it. For the big radius, which is y equal to x squared plus 1, we have to solve for x. So we get x squared equal to y minus 1, and we get x equal to plus or minus the square root of y minus 1. Which is it, the plus part or the minus part? Well, if we think about it, if we're over here in quadrant 1, is x positive or negative? Right, so it's definitely the positive part. But be careful. Sometimes they'll give you a graph where you actually have the other side of it, and so you would have to use the negative part instead. So that's what we're going to get. We're going to get x equal to the positive squared by 1. So this would be pi times the integral from 30 to 40 of the square root of y minus 1 squared I guess it wouldn't really matter whether it's positive or negative because we're going to square it in these examples. Minus, that's a much better question. Am I sure I read it right? I did read it correctly, unfortunately. Yeah, well, I mean, yeah, so this one would be a lot nicer, right? Pi integral from 30 to 40, y minus 1 minus y squared over 100. And then we would do the usual sort of stuff. So not as bad. Again, not what you're being asked to do, but so there's not a lot else to say about volume, really. It's kind of this idea of just you've got a region and you're trying to think about what the limits of integration are and which functions further away. That's your larger radius, which function is closer, that's your smaller radius. There was one other problem I saw that I thought looked kind of terrible. So let's take a look at that one and then we'll see. Well, we're almost out of time, so we'll see. So I saw this question. Let R be the region bounded by y equals x plus 1 over 6, over 2, y equals 7x minus 6, and y equals 20 minus 6x. And before we get going here, we notice that all three of these things are what kind of graphs? Parabolas, circles. What are they? They're all lines. So that means we're probably going to have a triangle if we've got the region bounded by 3 straight lines. So let's see. We probably actually need to find where they intersect. I really don't want to, but I guess I will. So setting these two equal to each other, x plus 1 over 2 equal to 7x minus 6. Multiply everything by 2. X plus 1 equals 14x minus 12. I mean, I will say this is a time where you could just use Desmos. But if someone asks you this question on an exam, you won't have Desmos. So you might also want to practice doing the work of finding the points of intersection because you might actually have to do it at some point. And here this works out pretty nice. You get 13x equal to 13. So x equals 1. How nice. So these intersect at the point 1, 1. And then setting these two equal to each other, 7x minus 6 equals 20 minus 6x. Adding 6x, you get 13x. Adding 6, you get 26. How nice. Someone thought about this question and gave you nice numbers. So x equals 2 and y equals 2 times 7 is 14 minus 6 is 8. So 2, 8. And then finally setting these two equal to each other, 20 minus 6x equals x plus 1 over 2. Again, multiply everything by 2. 40 minus 12x equals x plus 1. 13x equals, oh, what a surprise, 39. So x equals 3. So our point would be x is 3 and y is 3 plus 1 over 2, which is 2. Cool.
Sorry, can you just give me a basic algebra recap on how we know that the first one is 1, 1?
So I know it's 1, 1 because I took this x value and I plugged it into either of the lines I said equal to each other.
I got it.
Same deal here, right? I took this x equals 2 and I plugged it into either of the lines, so on. Yeah. So now we can graph this thing, which I'll probably do it well final here. So we know we've got the point 1, 1, 2, 8, and 3, 2. Which we could graph the entire lines, but we really just need those segments. Now this line here is the line y equals 20 minus 6x. This line right here is the line y equals x plus 1 over 2. And this line here is the line y equals 7x minus 6. Now, let's actually talk about finding the area of this first, just because I think it's interesting. If you're going to find the area, you could use vertical or horizontal cross sections, but no matter which way you pick, you're going to have to break it up into two integrals. Because if you use horizontal cross sections, you've got a break point right here, where below that, your right function is this, x plus 1 over 2, and your left function is this, 7x minus 6. But then above that, your right function is now this, and your left function is now this. On the other hand, if we use vertical cross sections, you have the same sort of issue. We have a breakpoint right here. If you're going from left to right, in this section, the top function is 7x minus 6, and the bottom is x plus 1 over 2. Whereas in this section to the right, the top function is changed. So this sort of problem, no matter which way you slice it, you're going to have to write as two intervals for sure. Now, this particular problem says we want to rotate it around the x-axis, which is good. Why is it good? Well, because our functions are already functions of x. And if you're going around the x-axis, you want them to be functions of x. So that's why it's good. We don't have to change anything to something else. Okay, so we're thinking about vertical cross sections. All right, I want all of you to try and set up the integral for the volume of this first part. Oh, sorry, I missed that comment there. Let me look back and I'll look back and see for a second. Oh, you're right. I did say it was x squared plus 21, but I definitely wrote x squared plus 1 on that last problem. Yeah, good call. So just so everyone can see, I did make a small mistake on the last problem. When we're going on the y-axis, I wrote x squared plus 1. It should have been x squared plus 21 because that's what this function actually was. And so this should have been a little bit different. This would have been y equal to, or x squared equal to y minus 21, and x would have been plus square root of y minus 21. Good catch. Thank you. Sorry, I didn't see that earlier. So it would have been a little bit different. All right, if you ever say a thing in the chat or see something I like and totally go by it and I miss it, you're welcome to yell at me like, hey James, this is a thing. Stop. Speaking of things, let's look at this. So for this region here, again, so I want to say more, but I don't really have to. So sometimes people in other classes talk about revolving regions around other axes other than the x or the y axis. None of your homework problems have that. So I've avoided talking about it because. But what I would say is, whenever you're revolving around an axis, the bigger radius is always the difference between the function that's further from the axis. So when I look at this strip here, this function is the one that's further away from the axis of rotation. So that's my outer radius. So my outer radius is 7x minus 6. I'm squaring it. That's my big R squared. Minus, in this region here, my small radius is the function that's closer to the axis of rotation, which is x plus 1 over 2. And again, it's going to get squared. That's my little radius squared. And my limits of integration are how far left to how far right, which in this case is 1 to 2. For the next one, same idea. We're going from 2 to 3. And now the small radius is still the same function, but the big radius is changed to this other line. So it's going to be 20 minus 6x quantity squared minus still x plus 1 over 2 quantity squared. That's your big R squared in the second region. That's your little R squared in the second region. Yeah. And then you have to actually integrate it. So integrating it's not too terrible, but it's not wonderful. I will once again point out that if you wanted to make it maybe slightly less terrible, you could write this as the integral from 1 to 2 of 7x minus 6 squared plus the integral from 2 to 3 of 20 minus 6x squared minus the integral from 1 to 3 of x plus 1 over 2 squared. It's really just so you don't have to write out like the integral of this twice and keep track of all the things and plugging in the 2 and the 1 and the 3 and the 2. So you can do that. It does make it a little less calculation intensive. Question. Is it better to do a U sub for each of these, or is it better to multiply them out? I don't have a good answer to that question. I think you can make a convincing argument either way. It's probably more straightforward to multiply them out though. So if we multiply them out, it looks like this. 7x minus 6 squared is 49x squared minus 42 is minus 84x plus 36 dx plus this is going to be 20 squared minus 120x minus 120x. And this one's going to be, I would for this last one, bring out the 1/2 squared in front. So write it as 1/4. Integral from 1 to 3 of x plus 1 squared is x squared plus 2x plus 1. It's going to be a lot of bookkeeping, right? That's not pretty. Now, just to kind of maybe convince you that doing it the other way is going to be easier for you later on. Instead of doing this, just to show you how this one will work the other way, you could do this. You could say, or let u equal 7x minus 6. Doing a u sub for this one here. Then your du is going to equal 7 dx. So your dx is 1/7 du. So look how this part's going to change. Instead of doing all this, it's going to be the integral of, well, it's going to be dx is going to be 1/7 du. Instead of having 7x minus 6 squared, I'm going to have u squared. And I could even, and I should even change my limits of integration. Instead of x equal to 1, I'm going to get u equal to what? Feels kind of dumb. 1. Instead of x equal to 2, I'm going to get u equal to. Yeah. Okay, I have to kind of say, I think that's a lot easier to calculate. Right? If you do this, it's going to be 1/7 integral of u squared is u cubed over 3 from 1 to 8. And although the numbers still kind of suck, that's 1/21 times 8 cubed minus 1 cubed. That's a lot easier to actually physically calculate than doing the integral of this, the integral of this, the integral of this, and plugging in 2 and 1. So I would encourage you for this problem, which is problem 13 on your next homework assignment in section 5.7, it might be worth your while to, once you get to the integration part here, to actually do the u sub for each of these integrals.